theory seminar or the seminar today. Today we have a regular visitor from Interface, old friend of myself and of this department. And we're happy to have Professor Hsin-Chia Cheng of UC Davis to give the opening seminar today. Now, although he's well known, but let's still introduce it. Professor Cheng received his undergrad degree from NTU-CTP, one of the best students in his class, and received his PhD from Berkeley at 1996. Then he went to Fermilab for his first postdoc term, and then received a McCormick Fellow at Enrico Fermi Institute at the University of Chicago. After a further stay at Harvard, he joined UC Davis as assistant professor. Actually, at that time, I think NTU, NTHU, and Academic Seneca all tried to recruit him. He decided on UC Davis, and in 2006, he received the Outstanding Junior Investigator Award from DOE. And at the end of this award, in 2009, he was promoted to associate professor. And in 2012, he's been promoted to full professor. So he's a very regular visitor, and we're very happy to have him here. And for this week and next week, although Professor Cheng won't be here, the title seems to be the same, so about compositeness of the Higgs boson. The title today is a little Higgs boson from a composite Higgs theory. So the floor is yours.
Okay, thanks for the introduction. And I want to say it's not little Higgs, no, it's just a light Higgs. Although the idea has some relation. Now this is based on a couple papers we wrote together with Bogdan Debrescu at the Fermilab, and my student Jia Yinggu, who just graduated this year and joined the new center in Beijing as a postdoc. Now we know that in the past few years, the biggest news and biggest is the discovery of the Higgs boson. Now we know its mass is about 125 or 126 GeV, and it has a very important consequence. For example, now the Technicolor theory without a light Higgs boson is ruled out. But now an important question is the next important question is to ask the property of the Higgs boson. In particular, we want to know whether the Higgs boson is an elementary particle or a composite particle. Now, usually people think the such a light Higgs boson is preferred to be elementary because one usually expect that the composite Higgs boson should be heavy. The reason is that the Higgs boson mass is determined by its quartic coupling. In a strongly coupled theory, one generically expects the coupling to be big, therefore, which translates to a heavy Higgs boson. However, there's one way to make it light. Just suppose there are some symmetry which you can protect its mass. For example, if Higgs rises a pseudo-number boson of the strong dynamics, then it may still be light. And this idea was put forward in '84 by Kaplan and Georgia. And then people didn't pay much attention until about year 2000 or after. Then it got a lot of attention. Then many models which based on this idea has been proposed, like little Higgs theories, holographic Higgs, composite Higgs. I think even the gauge Higgs unification is very closely related to the same idea. Now, however, to get a light Higgs boson is not the only problem for a composite Higgs model. In fact, for anything that Higgs is not elementary, the large top Quark mass is also challenging for this type of model, because we know the top Quark mass is quite heavy. Now, if the Higgs is not elementary, for example, it's a fermion bilinear, then it has dimension 3. Then if you want to write down Yukawa coupling, naively you expect it coming from a higher dimensional operator. If it's suppressed by large scale, then the Yukawa coupling will become very small. This is good for the light generation, but for top Yukawa coupling, this is not good. The scale which suppress this high dimensional operator will be too low, and it will generate large flavor changing, neutral current, and so on. And there are many problems. So how do we accommodate a large top Quark mass in such a model? Is also need to be addressed. Now there are different ideas which are also similar. One idea is based on partial compositeness, which was proposed by David Kaplan in '91. The idea is that you propose an elementary top quark which mixes with some composite operator from the strong dynamics. This composite operator has the same quantum number as the top quark, so that you can write down such a mixing term. Now, due to this mixing, so the top quark is partially composite, therefore it can have a large coupling to the composite Higgs. Now, for such a model, there's a prediction is that in general, one expects this composite operator will produce a tau of resonance, just like a QCD. So since they have the same quantum number as the top quark, so they will produce, you expect to see a heavy top-like resonances in such a model. Now, another idea is just directly consider that the Higgs itself is just a bound state of the top quark. Now, this idea was proposed in '89 by Nambu and also Miransky. At that time, the top quark was not discovered yet. People only know it's very heavy. So they are thinking that maybe the heaviness of the top quark is related to the Higgs, and the Higgs in fact is a bound state of the top bottom, left-handed top bottom quark, right-handed top. This is in that case, one expects a large coupling between the Higgs and its constituent. So let's focus on this idea of the top condensation. Now, usually one assume that the strong dynamics which binds the top quark together can be, say, described by approximately described by this four fermion interaction. Some coupling suppressed by some dimensional scales, and the side L is the left-handed top-bottom doublet. Now, of course, this is not a complete theory, just effectively parameterize some strong dynamics. Now, if you want to go to a more complete theory, you have to say where does this interaction come from. For example, one can imagine that there are some new physics that has scale where when you integrate it out, you generate such an operator, like the top powder type model where you have two SU3, one for the first two generation, one for the third generation. This third generation one is the coupling is very large, but it's also spontaneously broken down to the diagonal one. Then one can, through this exchange of the heavy gauge boson, one can generate operator like this type. But in this talk, we will not be concerned about what the underlying physics is. So we will just start from this effective four fermion interaction to study its consequences. Now, this idea is basically based on the Nambu-Junang-Arseniev model, if you know, which Nambu got his Nobel Prize from. Now, the assumption is that when the coupling is large, then it can, due to this attractive force, it can form bound state between the right-hand top and the left-hand top-bottom doublet. Now, this bound state has the same quantum number as the Higgs field. So that one may imagine this Higgs field, in fact, is just this bound state. Another important requirement for this dynamics is that the four fermion interaction should not be confining, because we want the top quark is still the lowest degree of freedom. We don't want the QCD-like dynamics where the constituent is confined into the bound state. Now, if for such a theory, it is because at low energy, this interaction becomes irrelevant, becomes weaker. So it's not a confining theory. Now one can write down at the cutoff scale, this Higgs is not the dynamical degrees of freedom, but we can write down an auxiliary Higgs field by writing a mass term and this Yukawa type coupling. And then you integrate out this Higgs, and then you generate this full Fermi interaction we wrote down before. But that below the cutoff scale, because of the interaction, in fact, you generate the kinetic term for this composite field, like this. This one loop fermion diagram, you can generate this kinetic term for the Higgs, and also it will renormalize the mass of the field. Also at one loop, if you put four Higgs field outside, you can generate this quartic term. Now at the lower energy, you produce this kinetic term. Therefore, at the low energy, the Higgs becomes a dynamical degree of freedom. The mass term got renormalized by the fermion loop. It has a minus sign, so it reduced its mass. And this is the quartic coupling. One can see that if this term is bigger than 1, the Higgs mass square becomes negative. Therefore, it can trigger the chiral symmetry breaking. Therefore, the Higgs will get a non-zero vacuum expectation value. Therefore, break the electroweak symmetry. Now, this critical coupling is given by this number. So if G is bigger than that, you can form this bound state will get a bed. Okay, in fact, one can just, since they are all related by the same parameter, one can calculate what this, at the low energy, after you go to the canonical normalized field, you can calculate the Yukawa coupling. Top Yukawa coupling given by this formula. A pi square over NC. NC is number of color. Log lambda over mu. Lambda is the cutoff scale. It's the composite scale where this is strong dynamics, right? Mu is the low energy scale where we will take as the chiral symmetry breaking scale. Usually we don't if we don't want the large hierarchy between these two scales, say if the ratio is of order 10-ish, you find this Yukawa coupling is about 3.5, something like that, between 3 and 4. Now, in that case, you get a prediction of top quark mass to be about 600 GeV. Now, of course, we know this number is wrong, right? Because the top quark is about 173. When the model was proposed, of course, the top was not discovered yet. At that time, it was okay. Now, after it's discovered, then obviously this prediction is wrong. Now, this is not the only thing wrong with this model. The Higgs boson mass is also wrong. Because Higgs quartic coupling, one can also calculate in this model. Now, in the leading NC approximation, basically you only include the fermion loop. Then you can calculate, you find the Higgs quartic coupling is just twice of the Yukawa coupling square. This translates into the Higgs boson mass to be twice of the top quark mass. It's just twice of the computational mass. If top quark mass is already 600 GeV, the Higgs mass is above 1 GeV, which is also badly, very bad prediction.
I'm sorry, Hsin-Chia, if you raise the cutoff,
yes,
did you get top quark to be 120?
Yeah, so one can see that if you can raise the lambda, you can reduce this Yukawa coupling, right? Of course, at the expense of the tuning. In fact, when you raise this, you shouldn't rely on this one loop result. You should use the RG evolution to sum overall diagram. In fact, this was done by Hill Linder in 90. Indeed, you can reduce their mass, but even if you raise the lambda to the Planck scale, they are still too heavy. The top quark mass is still above 200 GeV. The Higgs mass is above 300 GeV. Their ratio is governed by a quasi-infrared fixed point, roughly 1.5 or so. So even if you are willing to tune this model, they are still too heavy in this case. So we have these two problems. So for people which will not give up on this idea. We'll try to always find a way to fix that. There are different ideas how to fix this problem. And one of the solutions is so-called the top seesaw mechanism, proposed by the Brasco and Hill in '98. What they do is if the top quark mass is too heavy, then we just try to reduce it by mixing. So they introduce a vector-like singlet quark, chi-L and chi-R. In fact, they have the same quantum number as the right-handed bottom quark. In fact, chi-R and the T-R have the exact same quantum number. So there's an arbitrary rotation between them. You just call it one chi-R, one T-R. Now, without this new quark, you have this term, which let's concede is too big, 3.5 or so. Now, because they have the same quantum numbers, right hand and top, you can just write down vector like Dirac mass between them. Right? Also, because TR has the same quantum numbers, chi, you can also write down the Dirac mass between chi-L and the TR. So these are these two terms. Okay, these are allowed. So for the mass matrix between the top quark, the left-handed top quark and the right-handed top quark, you have this 2x2 matrix. Now this entry you know is about 600 GeV. If you assume the composite scale is not too high. Now these two are somewhat arbitrary, so you can always choose these two numbers. Choose this to be somewhat bigger than that one. So you have a seesaw type matrix. Through the seesaw mechanism, you can get a light eigenstate, and then you just choose the appropriate number, so that the light eigenstate will be correct to the top quark mass. This is one way to save this type of model. But what about the Higgs boson mass? Now, 991 still expects this model will have a very heavy Higgs boson. In fact, Chris Hill, after the Higgs discovery, he went out to give many talks saying that the top seesaw model is ruled out. Now, what we were telling him just to say it's too fast. It's not yet ruled out, because if you take this model really seriously, you find that in fact this model can have enhanced global symmetry, because you have the left-handed T left and B left doublet, and you introduce this chi left. If they are all intact under this new strong dynamics, there can be a global U3 symmetry which transform among them. Now this global U3 symmetry will be spontaneously broken once you break this chiral symmetry. Now the Higgs field can arise as pseudo-Navier-Wilson boson from U3 broken down to U2.
So for the deep quark, you use criticality to maintain it to be light?
Well, in this case, if you don't include the right-handed top quark, the right-handed bottom quark at this level, right-handed bottom is, the bottom is the massless. So this is a detailed model question. Basically, whether you want to include the right-handed bottom into your strong dynamics or not. If you don't, then it's massless. If you do, then you do require some new interaction to distinguish the right-hand top and right-hand bottom, such that the right-hand top is supercritical, but the right-hand bottom is subcritical, as you said. This may require some tuning. But the focus is, well, here we are not talk too much on the bottom. Here we just assume it's massless for the moment, and its mass coming from the higher dimensional operator.
The underlying question is isotherm breaking. So if you really consider the full electroweak theory, then
the weak iso spin breaking.
Yeah.
In fact, this will be the strongest constraint of this model. If you want to make it less tuning, you need to extend this model, which I plan to talk about after the simple model, but it depends on how much time I have. Okay, so let's see how this idea works. Now we assume the underlying non-confining strong dynamics approximately preserve the U3L cross U2R symmetry between these fields. Here we are interested in the left-handed top-bottom doublet and the left-handed chi in new Quark, and the right-handed top and the right-handed chi. In fact, U2 is not important. We will break it strongly. So only U3 is the relevant thing. So therefore, we write this 6 scalar field as phi t and phi chi. Each one is a triplet. Okay, under this U3. Now the label looks like this. Phi t is made of HT, which is a doublet, and phi t is a singlet. This is the bound state between T right and this left-handed fermion triplet, and the phi chi is this thing. We will assume that the Higgs is mostly this guy. In fact, mostly the bound state between the left-handed side left and the chi right. Here you say, well, you have chi right and T right are just some label, since they have the exact same quantum number. So it doesn't matter which one we call it. Chi right or T right. It's just after Seesaw mechanism, mostly the top right is more of this than this. That's why the label is in this way. Now we have the Yukawa interaction. After that, you form the bound state. You have the Yukawa interaction between the bound state and its constituent fermions like this. And also you generate the scalar potential. These are the quartic terms generated from fermion loops. There are 2 types. You can write down. In fact, a fermion loop only generates the first type. Now this one can be induced through additional scalar loop. So in general, this one is much smaller than this term. And you also have the mass term for the scalar. Now, so far these potentials are exactly symmetric under this symmetry. Of course, we need some explicit symmetry breaking to generate potential for the Higgs. So we introduce symmetry breaking terms. We will assume large U2 breaking from the mass term. For example, the phi t and phi chi will get very different masses. But since the mass square are quadratic sensitive to the UV physics, it's easy to generate such a big splitting. We will assume that the splitting is such that only this one has a negative mass square, where this one, the mass square stay positive, so that the chiral symmetry breaking mostly occurred in this Light Higgs sector. You can also have mixing term and so on. Now for U3 breaking, well, since we introduced this vector-like fermion, we can write down this vector-like mass as we did earlier. This mass, in fact, in the low energy effective theory, they translate into typo term of the scalar field, since the scalar is just unstate of the sky. So these are typo term of the singular component of this field. Since chi right and T right have the same quantum number, we can always do an arbitrary rotation. We can either rotate out this mixing term, or we can rotate out this fermion mass or this typo term. We will do the rotation, which will remove this term. It's more convenient for discussion. Now, after that, you can write down the total effective scalar potential. And the dynamical assumption is that only m chi square is negative, where MTT square is positive, so that the chi will get phi chi will get a non-zero vacuum expectation value. On the other hand, due to this typo term, this singular component of the scalar also get a non-zero vacuum expectation value. So one can minimize the potential. One can find that we can find a minimum with the vacuum expectation value looks like this. The biggest wave is from here because this one get a negative mass square. So this is spontaneously break this chiral symmetry break. It's chiral symmetry. On this one, get a wave due to the tapo term. We already removed this tapo term. Remove the tapo. Then due to the mixing, this will also induce a wave for the doublet component of this phi chi field. So this will be identified as a Higgs field. Now here we have some just simple UT, well we will call U times sine gamma and U chi as U times cosine gamma. Then they are, after you minimize them, then you find a relation like this. That since this model has two Higgs doublet, right? One coming from here, one coming from here. This one is the light Higgs. This one is the heavy Higgs. The heavy Higgs will have some charge Higgs component. Its mass is mostly related to this mass plus some additional contribution. And the other relation like this. Another important point is this tapo term is also related to this charge Higgs mass and the sine gamma. Basically, if UT is 0, this term is also 0. We can see that this term controls the wave of this phi t. Now we can write down the charge 2/3 fermion mass matrix. In fact, one finds that it exactly take this top seesaw form. This is the coupling. This is the wave which into electric braking wave, which should be 246 GeV. Now these are the wave in the singular component. So one just need to choose our sine gamma such that you get a light eigenstate of 173 GeV. This turns out to require this sine gamma to be of close to like a 1/4 to 1/5, which is given by the top. The measure of the top Yukawa coupling divided by the strong top Yukawa coupling. Now there's a heavy top partner T prime with mass about this c times this chiral symmetry breaking scale. So this one will be quite heavy. So after the fermion mass, one can examine the scalar mass, whether we get a light Higgs boson or not. Now first, since this model has two Higgs doublet and two singlet, so it has total 4 CT event scalars. They are labeled like this: H, T, H chi, they come from doublet, phi T, phi chi coming from singlet. This one is mostly the Higgs boson, as we said. The whole mass matrix looks like this. It's a huge matrix. Remember, all these quartic couplings are large. So if you don't have the mixing, you just have this term. In fact, the Higgs boson will be very heavy because the quartic coupling is very large. Now, through this mixing, that reduce the Higgs boson mass, you can diagonalize this matrix to find the lightest eigenvalue and give an approximate analytic formula looks like this. This may not be very transparent, but you can factor out different things. You find that it can be written in this way. This part is nothing but top Scalar coupling times wave. So this is related to the top Quark mass. Now there's a factor, overall factor, lambda 1 over 2c squared. This factor is less than 1. It's close to 1 when the charge Higgs mass is very heavy. But when it's less than 1 factor. Now this is in the NGL cap model. In the leading NC approximation, we say earlier, it's just 1. Right? Before we say that the couplings, the Higgs boson mass is more like a lambda 1 times v squared. Now you see this one now get a suppression like yt over to c squared. So this you see that there is a suppression factor too. Another way to write down is that the effective Higgs quartic coupling is given by this, again, this ratio times this factor, which is always smaller than 1, times yt squared. So the Higgs boson mass is closely related to the top Quark mass, and they are comparable of the same order. And one can understand this using the